Durham University of United Kingdom. Currently, Prantika is a postdoctoral research associate in the Applied and Computational Mathematics Group, Department of Mathematical Sciences, Durham University, UK. She is working with Professor Anthony Yates on computational modeling of the magnetic field in solar corona based on a magnetofrictional approach to determine the role of memory in building up the coronal magnetic structures and possible observational consequences. Prantika finished her PhD in 2019 from IISER, Kolkata, India, where she worked with Professor Dibyendu Nandi and studied the generation and evolution of large-scale magnetic fields in the solar interior and on the surface by developing new computational models. The primary objective of her graduate research was to predict sunspot cycle 25. And we have listened to that talk in a couple of years ago, that paper she published in Nature. And today, Prantika will be presenting one of her newest research on two classes of eruptive during solar minimum. So, to Prantika, you know.
Yeah, I'll share my screen. Can you see the slide?
Yeah.
Okay, that's great. Thank you for inviting me, and yeah, it was like a great opportunity. And I was supposed to go visit, like at least there in Colorado, but suddenly due to some unforeseen circumstances, I had to cancel my plan to visit the US. Nevertheless, so today I'll be talking about two classes of eruptive events during solar minimum. So this work I'm doing here as a postdoc with Anthony Yates using a magnetofrictional model. So at any point of the talk, you can stop me and ask questions. So I'll start now. So we know that the coronal mass ejections are one of the primary factors causing adverse space weather conditions, and CMEs are often associated with complex magnetic structures on the sun, such as active regions. So if we see the evolution of number of sunspots over time, it roughly follows an 11-year solar cycle. And if we compare it with the CME rate, like the number of CMEs per day, it again roughly follows the 11-year sunspot cycle. So it is, you can say like these CMEs are quite closely associated with these active regions. Another source of CMEs is eruption of filaments or prominences. And within a filament, a bundle of magnetic flux field lines twist themselves around a common axis, forming flux rope structures. And magnetic flux ropes are often associated with the filaments or prominences. Now, if we consider the time evolution of the number of filaments, those appeared in the lower part of the corona, we again see that common 11-year solar cycle. However, during the solar minimum period, when there is hardly any sunspot present on the solar surface, we still can find few number of filaments present in the lower part of the corona. Now, if we compare this with the number of CME evolution, we can speculate that few of these CMEs, those happened during the solar cycle 23 minimum, was in fact linked with eruption of few of these filaments. Now, to understand why the filament eruption happens, so what happens, like surface evolution generates non-potentiality in the coronal magnetic field, which leads to growth of magnetic free energy that becomes concentrated within these flux rope structures associated with the filaments. Now, under certain circumstances, these structures can become unstable and trigger eruption of filaments, thus producing solar flares or coronal mass ejections. So, to understand the evolution of such non-potential structures, we must need a time-dependent non-potential coronal magnetic field. For that purpose, we use the Dumfries code, which is a global non-potential coronal magnetic field model developed based on magnetofrictional approach. In that model, we solve the magnetic induction equation in terms of vector potential, and we use the non-ideal form of the magnetic induction equation, where A is the vector potential, E is the electric field. And then electric field has two components. One is like the V cos B term. V is the velocity and B is the magnetic field, and another is the non-ideal part of the induction equation. Now, velocity in the corona again has two components. One is the frictional velocity, where it is proportional to the Lorentz force J cross B, and it causes the magnetic field to relax towards the force free equilibrium. It has another component which is like shown by this V out, which mimics the presence of solar wind present in the solar corona. Now, at the bottom boundary of this magnetofictional model, a surface flux transport model is parallelly running. Now, the non-ideal part of the induction equation, we primarily model it using hyperdiffusion, which helps in removing gradient in non-potentiality measured by alpha, which is equal to J dot B by B square. And now, as I was saying, so there is one surface flux transport model that is running parallelly at the bottom boundary of this magnetofictional model, such that the global coronal magnetic field evolves in response to the large scale shearing velocity on the solar surface. So the global coronal magnetic field is never in a force free equilibrium. So moving on to to this particular study, we performed a magnetofiction simulation of 180 days period, quite close to the solar cycle 24 minimum. We started with a potential field source surface extrapolation on Carrington rotation map 2207, and we assumed that during that 6 months period, no new sunspot emerged on the solar surface to keep our study as simple as possible. And because of that assumption, we missed 13 sunspots during that period. So the results of this study can be divided into two parts. So in the first part, we study the evolution of global measures of non-potentiality, and then the second part, we study the evolution of individual non-potential structures in the corona. So, what are the global measures of non-potentiality in the coronal magnetic field? Such measures can be coronal magnetic free energy, current density, magnetic helicity, etc. So this particular figure is showing the evolution of magnetic free energy and current density over the period of our simulation, that is 180 days. And as you know, like the free energy is the expendable energy for eruption of flux ropes or those non-potential structures. So as you can see, during the first 50 days, this free energy as well as the current density rises. So this can be considered as the ramp up time, which is necessary for the global coronal magnetic field to evolve far from its initial potential field configuration. Beyond this 50 days period, you can see there are certain instances where both free energy and current density drops suddenly, and those are marked by this set of vertical lines. So now free energy and current density is global quantities, and it cannot describe or cannot reveal how this non-potential energy is spatially distributed within the global corona. To understand that, we use the concept of magnetic field line helicity, which is calculated by using this particular formula. So, magnetic field line helicity can be considered as flux linked with the magnetic field lines, where it considers contributions from two things. One is twisting of magnetic field lines with height, another is winding around centers of strong magnetic flux on the boundaries. So, in this series of figures that you are seeing on the left, so the gray background in the top panel is showing the photospheric magnetic field, the radial component of the photospheric magnetic field, and on the top of that, the magnetic field lines is color coded according to their field line helicity. So red means positive and blue means negative. So now if we take a photospheric projection of the magnetic field line helicity, we can generate a plot which is shown in the middle panel. As you can see, there are certain locations where the magnetic field line helicity becomes concentrated. So if we apply threshold on this middle panel, we can extract out the regions with strong magnetic field line helicity. Naturally, those regions which are shown in the bottom panel can store significant amount of magnetic non-potential energy. So as you can see, over time such structures form and sometimes it disappears also. What I mean by disappearance of these non-potential structures, I will explain in this slide. So these are magnetic field line maps upon two dates. One is on day 148 in our simulation and day 152. So between these two dates within this black rectangle, you can see this set of blue field lines disappeared on the second date. And in the footprint map of the structure, we can see this blue structure disappeared completely on the second date. Now, if this was a case of eruption of non-potential structures, naturally we should see some signatures in the we should see some changes in the open magnetic field distribution around that structure, and that we find in the coronal hole map area. So the coronal hole map is according to the distribution of open magnetic field lines. The green here means like the open magnetic field lines are going outward, and the light magenta one is like the magnetic field lines are going towards the surface. So as you can see, between that those two dates within this black rectangle, this green patch disappeared. So if we consider the change in coronal hole area, which I am showing by this middle row, so the green patch here means like increase in the coronal hole area. So as the structure is moving towards the upper boundary of the corona, so the magnetic field lines which were like encompassing it will starts opening up. So that will increase the coronal hole area. As the structure erupted or left our simulation box, so then the magnetic field lines again will start closing down. So that should decrease the coronal hole area, and that is what we are finding at the end of the event by this magenta patch. Another thing is magnetic field is in the corona is primarily radial because of the solar wind. However, if there is a non-potential structures which is emerging from the lower part of the corona and moving upward, we should see an enhancement in the horizontal component of magnetic field associated with the structure at the top boundary of our simulation, which we have set as at 2.5 solar radii. And naturally we see like at the initial stage of the event and enhancement in the horizontal component of magnetic field at the top boundary, and after the event that like that concentration of the horizontal component of magnetic field diffused away. So all these signatures indicates that probably there was that the evolution of that structure was a case of flux trough eruption. So again, going back to the global picture, we can see in the first plot is like the evolution of magnetic free energy and current density. We see there like at certain epochs, those two quantities undergo sudden decrease, and at the same epochs, the magnetic field and helicity also reduced. And these red spikes, you can see those are representing the enhancement in the horizontal component of magnetic field in the top boundary, and in the bottom panel this magenta curve is showing the open flux. So as you can see, all these sudden changes are happening simultaneously at those certain epochs. So we can say during those time the non-potential magnetic field structure at some part of the corona undergoes like certain drastic changes. Another thing that we calculated is like the presence of positive tension force. So as I was saying, within the filamentary structure, the magnetic field lines has like helical configuration. So within that kind of helical configuration, it's very natural to have positive tension force, as you can see in this figure. So we also calculated the positive tension force at 2 solar radii, and we find that at certain point or for certain cases, we found the signature of positive tension force as well. So we identify 19 such instances where all these signatures were happening simultaneously. Now the question is, do all these events indicate eruption of flux troops or not? That leads us to the second part of our study, which is like how these individual structures evolve over time. And we find that actually there exists two distinct class of evolution. So first, I'll be talking about the event that how this particular structure evolved over time. As you can see, I already mentioned. So this blue structure disappeared completely on the second date, and it was associated with these drops of free energy, current density, magnetic field line helicity, or enhancement in the horizontal component of magnetic field at the top boundary. So we studied the 3D evolution of the magnetic field lines associated with the structures. So this the color of these field lines are based on their field line helicity content. So darker is the color, it means like it has more non-potential energy. So as it evolves over time, we can see the helical structure associated with the flux troops to form. Then it becomes unstable. Just before becoming unstable, we see a clear U-shaped loop forming. Then the whole structure erupted, And after the end of the eruption, we see low line magnetic field lines are forming at the lower part of the corona, which hardly has any magnetic helicity. So this was an uh, example where the flux group erupted completely and it disappeared, and it indicates a full scale eruption. So it can explain the occasional filament erupting CMEs that we observed during the solar minimum period. So now moving on to the second kind of eruption. So I will be particularly talking about another event which is shown by this magenta vertical lines here. So as you can see, during that time also there is a drop in helicity, also in current and free energy, as well as and peak in the horizontal component of magnetic field at the top boundary. So the structure associated with this particular change is shown here. So between the day 74 and 77, we see this red structure here shrunk quite a bit, or the size reduced quite a bit on the second date. So, but when and this was also the change in that structure was also reflected in the coronal hole area distribution. As you can see in the initial phase, we see enhancement in the we see like increase in the coronal hole area as shown in the by this green patch, and then at the end of the event we see decrease in the coronal hole area shown by this magenta patch. And again, that event was associated with the initial enhancement of the horizontal component of magnetic field at the top boundary, and then after the event that this enhancement diffused away. But when we see the 3D evolution of that particular event, we find that initially there was quite overline sheared arcade at the top boundary shown, which has like significant amount of field line helicity. And as it evolves over time, we do not see any helical structure to form. Rather, we see this overline sheared arcade starts opening up. And then we find also there exist low line fill lines with quite significant helicity in the east-west direction, but that remained almost unaltered throughout the evolution of the whole event. At the end stage of this event, we see like new arcades of almost no potential nature starts forming on the top of that shared low line fill lines. So we find that in this event it undergoes partial helicity shedding through reconnection in the overlying arcades with surrounding magnetic field before settling down to a relatively more stable structure. And it is quite similar to the events like streamer blowouts, which are often considered as one of the potential candidates to explain the source of stealth CMEs. So in the next part, what we did, we tried to find out whether among these 19 events, we find that 8 of those were like flux drop eruption cases, and the remaining 11 were like cases of overlying arcade eruption. And we tried to find out whether they have other differences, such as we calculated the footprint area, then magnetic flux and helicity magnitude associated with those events, as well as the change in magnetic flux and change in helicity magnitude during those events. And the general the commonality that we find that in all those for all those quantities were higher in case of flux drop eruption as compared to the overlying arcade eruption. In particular, change in magnetic flux and change in helicity magnitude was quite higher in case of flux drop eruption event. Now, another distinct difference that we find is like the presence of positive radial tension force. As I was saying, so in case of flux drop eruption, because the magnetic field has that helical configuration, there is positive tension force present within that structure. But in case of overlying arcade eruption, because there is no helical structure, we do not find any positive tension force. So as you can see, like in the bottom panel, these black curved black peaks are only present in case of flux of eruption events. Now the presence of this now the question arises like whether this presence of these two distinct classes of evolution is somehow dependent on our choice of parameters in our code, or the way we model the non-ideal part of the induction equation. So we have seen that even if we use like Bhowmick diffusion instead of hyper diffusion to model the non-ideal part of the induction equation, or we use a slower solar wind in the corona, we still find the existence of these two classes of evolution. So our result is quite robust in that sense. So this is like in a way the summary slide. So we performed 180 days of global coronal magnetic field simulation using the magnetofictional model. Our study period was quite close to the solar cycle 24 minimum without considering emergence of any sunspot. Still, we find that the corona can be significantly dynamic even without emergence of any sunspots, and that can lead to formation and disappearance of non-potential structures, as shown within this global measures. Further, the evolution of those non-potential structures can be categorized into two classes. In the first class, the flux group disappears entirely, indicating a full-scale eruption. This can explain the origin of occasional filament erupting CMEs that we see during the solar minimum period. And in the second class of evolution, the magnetic field associated with the non-potential structures undergoes partial helicity shading through reconnection in the overlying arcades with the surrounding magnetic field before settling down to a more relatively stable structure. And this second class of evolution is quite similar to the streamer blowout events, which are often considered as one of the potential candidates to explain stealth CMEs. So this work actually was recently published in Solar Physics, so you can read in greater details there. So now, since I have like a few minutes left, I think so I'll briefly talk about the other ongoing projects that I am doing now. So one is, as I was saying, this second kind of events was quite interesting because there you can see like it holds all the signatures of or showing it all showing many signatures that through this kind of events the global corona is shedding quite a bit of its non-potentiality, like decrease in the mean field line helicity or free energy and so on. However, we do not find any helical structure there. So if there is no helical structure, there is a possibility that there will not be any filamentary material within, like associated with such structures. And as we know that stealth CMEs are often considered are called like stealth CMEs because they do not have any observational signature in the lower part of the corona. So we are thinking like this kind of events can probably consider as one of the potential candidate to explain the stealth CME. So that is one project that I'm working on, and like it's almost done. So I'm writing the manuscript now. So where we use both 2D magnetofiction simulation and 3D magnetofiction simulation to explore the origin of stealth CMEs. And another major project that I am now currently involved in is like the global evolution of non-potential coronal magnetic field driven by active regions. So the work that I explained so far was a study quite close to the solar cycle 24 minimum, and where we did not consider any sunspot emergence, but to but in this particular project we are actually considering the emergence of sunspots also. So what we did, we are studying a period quite close to the solar cycle 24 maximum between like 1st June 2011 to till 31st December 2011, a period of 7 months, a very active period of the sun. And this particular image here on the right is showing the emergence of those sunspots during that period, superposed on the like the photospheric magnetic flux. So during that period, we find that 102 active regions were emerged, and this active region database we are we are generating the database of these active regions using the sharp HMI data. So just to explain briefly how we are modeling those active regions in the magnetofictional model, as you can see, this is like a sharp patch, and particularly this work is important because we are not approximating the active regions as like ideal bipolar active regions, but we are taking the shape or the size shape of the active region as it is recorded by the sharp. So what we are doing is like, as you remember, the magnetic induction equation was in terms of electric field can be written in this form. So we are calculating the electric field locally associated with the active regions, and we are introducing it through this equation here. So another thing we are doing, we are considering an emergence timing, so the TEM. So during that emergence timing, we are applying the electric field continuously on the photospheric boundary. And the And there is another vector potential associated with this active region, which is shown by this AEM. And this vector potential is such that if we take a curl of that vector potential, it will give the observed BR associated with the sharp patch. We also are considering like introducing the twist in the active regions. Like we have seen, like the active regions, mostly like the complex one, will have some twist in those. So we are modeling it in such a way that the resulting horizontal magnetic field will be proportional to the twist, that is tau shown by here. And we know that the twist of in these active regions often follow the hemispheric sign rule. Like the twist for the active regions emerging in the northern hemisphere will have negative twist, and it will have positive twist if it is emerging in the southern hemisphere. So we in general try to follow that rule too. And this particular figure is showing how the horizontal component of magnetic field is changing associated with the active region. So this middle panel is showing the vector potential when the twist is zero, and the last panel is showing the when the twist is minus 0.2. Yeah. So so now the thing is like the twist is not like recorded in observation. So we have introduced different values of twist associated with the active regions and performed in extensive parameter space study. We performed uh, additional simulations where the sign of the twist depends on the alpha value that is recorded. So I will discuss it in a bit. So just and another thing that we can see is like for how long this electric field associated with the active regions will be given. So that we found that we use like 6 hours or 12 hours or 24 hours, and we found that the 24 hours is like the most appropriate one because it's more similar to the what is observed. And another thing we found that even if we change the emergence duration, that doesn't affect the global picture that in that way. Only the lower emergence duration will generate higher current, but that diffuses away very quickly. So just to explain again, so like for this particular active region, this A, like the vector potential is showing, this particular one is showing when the twist is zero, and when we increase the twist, you can see this vector potential is enhanced. And this particular figure is showing the 3D view of the twist. So as you can see, if we increase the twist, the magnetic field lines associated with it in like becomes more helical. And as this spot was emerging in the northern hemisphere, we considered its twist to be negative. Another thing that we can do other than the hemispheric rule, so the closest observed quantity to the twist in our model is the mean alpha provided by HMI, and that is like J dot summation, that mean A alpha is calculated is proportional to the J dot B divided by B square. What we find that when we calculated or when we studied the observed alpha for those 102 active regions for our duration of our simulation, not all of them are following the hemispheric rule. As you can see, this middle panel is showing the mean alpha as a function of the histogram of the mean alpha. As you can see, even if they are appearing in the northern hemisphere, there are many active regions which has positive twist, and that is I find a similar scenario in case of spots which were emerging in the southern hemisphere. There are many spots which has like negative alpha even if they are appearing in the southern hemisphere. So one thing that we can do, we can choose the sign of the twist according to the observed sign of alpha. So we performed simulations varying those parameters also. So because this was a simulation where there were 102 active regions and it was quite active period, so it would have been very difficult to perform a similar study which I already talked about, where we studied evolution of individual non-potential structures. Rather, what we did in this particular study, we study the global measures of like we study the global quantities, how it evolves over time in our simulation, such as open magnetic flux, total energy, current density. Then horizontal component of magnetic field at the top boundary, which is like which we found as one of very excellent measures to see the non-potential nature of the coronal magnetic field, as well as helicity flux. So as I was saying, the horizontal component of magnetic field. So this particular figure is showing in the middle panel with these blue stars, is showing how the horizontal component of magnetic field is varying at the top boundary in the northern hemisphere, and with the red stars it's showing how it is varying in the southern hemisphere. And as you can see, if we increase the twist in the active regions, so there are the number of peaks increase quite a lot with higher increase in twist. So that is quite natural. As we introduce more non-potentiality through the active regions, there are higher chances of having more eruptive cases. So just to so this particular figure is showing if so this particular figure is showing how increasing the twist will increase the chance of having more eruptive events, as well as it is also showing how if we consider the sign like the hemispheric sign rule, like all active regions in the northern hemisphere will have negative twist and all will have positive twist in the southern hemisphere, compared to the cases where the sign will be according to the sign of the observed alpha. And we see in fact there is difference in those number of peaks. So the sign is quite important. This particular figure is like a conclusion figure, is showing how using different values of twist is uh, how different measures of non-potentiality such as like energy, current, helicity flux or horizontal component of magnetic field or peaks in the horizontal component of magnetic field is varying while we use different values of twist. So as you can see in the maybe it's like hard to see, but in the along the x-axis it is showing different values, like where twist is 0, then 0.5. 0.5 s means like where the sign will be according to the observed alpha. And there were other cases where I considered the twist to be proportional to the observed alpha values, not only the sign but also like the amplitude. And we find that the general thing is like if we consider the sign, if we consider like the sign of the alpha to determine the sign of the twist, in general all those quantities is a bit reduced compared to its the other case where the sign is strictly according to the hemispheric rule. So this is more like a comprehensive study. And another thing that we find, like if we use a very strong twist like 0.4 or zero point 0.2, there is a chance that the spot will immediately erupt as soon as it emerges. So there will not be a chance of slow evolution mm, of the of the non-potentiality associated with the spot. So the primary conclusion that we find that the increasing twist instigate more variation in the helicity flux as well as horizon or as well as the p perpendicular or the horizontal component of magnetic field at the source surface, but it doesn't impart that much difference in the open magnetic flux or the total energy, which are mostly dominated by the photospheric magnetic field strength. And there is another thing that we found that for twist which if that is much greater than or it is greater than 0.2, we observe immediate eruption associated with those emerging spot. And another thing that we find that after the initial eruption, the sign of the field line helicity in the extended diffuse magnetic field associated with the active regions are controlled primarily by the differential rotation and flux cancellation. Thus, the initial sign to start with associated with the active regions, even if that follows the hemispheric rule, at the latter stage of evolution, irrespective of the initial sign, like the differential rotation will take the dominating role to decide the sign. And then we find that with increasing twist, the number of peaks in the horizontal component of magnetic field increases, which is quite easy to understand why that is happening. And we find that the emergence duration, like for how long we are applying this electric field, doesn't have that much impact on the global evolution or the evolution of these quantities. And in future, we are now almost done with the other study also, where, as I was saying, whether we can model the twist in a better way. So we already, from the HMI database, we already have the alpha parameters associated with each active regions. So we try to parameterize the tau or the twist in a way that it will be proportional to the alpha, and which is the proportionality constant will be C. So what we are trying now is like calculating the alpha from our simulation using different values of C for these 100 active regions, and try to find the best C where the observed alpha and the simulated alpha will match the best. In that way, we'll have like a closer resemblance with the observed twist of the active regions. So this is like almost done, and we are also writing this paper too. So yeah, I'll probably stop at this conclusion slide. Yeah. Thank you. And I'd love to have your questions.
Sure, questions, please. Yuhang?
Yeah, thanks for a very nice talk. Can you go back to the view graph which shows the frictional model, the equations,
Yeah, sure.
with the velocity imposed? Very early, very beginning. Yeah. So I have a question with this V out radial velocity. So if you impose that, it's just a function of R. It seems that you will never be able to have any closed field. Everything will be dragged out. It's like, how do you get a equilibrium structure? For example, it's force-free equilibrium. But if you have that, isn't it going to you just continuously pushing things out?
So the way it is modeled, I'm sorry that I didn't put the equation. So it's the way it is modeled, like it will be almost zero, quite close to the lower corona, and it will exponent. Can you see this PDF?
Yeah.
Okay, yeah. So this is like the way we model the V out. So it will be very low, or like it will have very insignificant amount of effect if the structure is at the lower part of the corona. As we are going away from like towards the 2.5 solar day, which is like the upper boundary of our model. So then the speed will start rising exponentially. So that's why we'll still have this like closed fill lines quite close down to the lower part of the corona.
Okay. And I have another question.
Yeah, sure.
So in the first set of calculations, you said you don't have any emergence. Is that right? And then what is the source of the non-potentiality that gets created, that creates these eruptive structures? What is the source of your
It's like the shearing velocity on the solar surface, because like at the bottom boundary of this model, the surface flux transport model is going on. So there is like the differential rotation is there.
Okay, so it's the differential rotation and then diffusion, supergranular diffusion.
Exactly.
All right. Thank you.
So any other questions? Gabriel?
Hi, Prantika. Thank you for the talk. I just had do you mind going back towards the end of your talk where you were discussing how selecting, if I understand correctly, you had one set of simulations where you did not choose the correct sign for the twist, not the observed sign, and then you had a set of simulations where you did choose it, and that seemed to affect these global
measures.
Measures. And what was the outcome when you chose? Are the entries labeled with S the ones where you did choose the right?
Yeah, exactly. So the S is like where the sign is according to the observed sign of alpha.
Yeah.
And
so we find. Okay, great. So in the case of choosing the right sign, you tend to have lower total non-potential or free energy in the system.
Yeah.
And is that because the global field still has the preferred orientation?
Yes, because like the differential rotation has like quite profound effect on the overall global non-potentiality. As I found, like the initial part of my talk, I was saying like, okay, even if there is no active region, still just because of the differential rotation, this sign of helicity or the non-potentiality will be formed in these two different hemispheres. So when we are considering the sign of those active regions, in a way, like we are cancelling out the background non-potentiality, you can say. So if the sign is not according, so if the sign is same as the global sign in a way, which is imparted by the differential rotation, so that will act as a positive enforcement, you can say. But if the sign is like the other way around, so it will in a way reduce the amount. So that's why we
and
think like
and effectively sort of increase non-potentiality, because you're adding active regions that are twisted in a way that wants to reconnect with the global field. And I think you said that it does, because even the active regions that are twisted in the opposite way, they still end by the end of the simulation, they all get twisted, they all get reconnected. So it's almost like they're creating some extra friction in the system that effectively then becomes non-potentiality. I guess on the sun itself, the sign is usually obeyed, right? You get the
yeah,
two
it's
hemispheres.
usually obeyed, but you can see like for those 100 active regions, like about 100 active regions which we introduced. So this is just a sign of alpha. So the
Right.
majority, you can say, I mean, yeah. So in the northern hemisphere, this is like the negative. So there were like mostly, yeah, the majority, if you say, like it was negative in the northern hemisphere and it was positive in the southern hemisphere. But still, we find there were few cases where the sign, I mean, it didn't follow the hemispheric sign rule. So we were actually interested to know like what happens if we consider if we violate the hemispheric sign rule.
Great. Thank you very much for your answers.
Thank you.
Shara?
I have a follow-up on that. That's really interesting. And so so that's the sign rule that you can see in active regions and sigmoids and some other and filaments and things. So you were saying that the background, just the differential rotation, is that contributing? Is that helicity direction the same or opposite to this?
So yeah, that's like quite interesting. So it depends on like the phase of the solar cycle. So if it is like the initial phase of the solar cycle, the way the global magnetic field or the what can I say, like the polarity inversion lines where they are, and then in a way, so the helicity that will come from the differential rotation actually will not follow the hemispheric sign rule. But if it is in the declining phase or the second part of the solar cycle, then the differential rotation will correct or will give like the correct sign. So in a way, it's very important what we found. I mean, I should have mentioned about it. So if I am going back to this simulation, I mean, you will find because this was very close to the solar cycle minimum period and there were like no active regions, just because of the differential rotation, the helicity is positive in the northern hemisphere and negative in the southern hemisphere, which is actually opposite to what we should observe.
But what you observe with the sunspots, for example.
Yeah, with the sunspots, what we found that okay, it starts to correct its sign, like it becomes positive in the northern hemisphere, negative in the northern hemisphere, and positive in the southern hemisphere, because like those sunspots majority will have like negative twist in the northern hemisphere. So that like a long simulation we are also doing, but we still have not quite, like we are doing a full cycle simulation starting from the beginning of HMI era. And we are actually saying like we have quite passed the solar maxima and we found that okay, it's actually correcting the helicity sign.
So I've seen, and this is really interesting on many different levels. The Macintosh archive of filaments and polarities. We've made some movies. Annie helped us make a movie, Annie Malonyshenko, of looking at it from the North Pole, and it's quite interesting because you can see it kind of spitting up and spitting down in a weird way, which you can sort of visualize. But I think it must be the same thing you're talking about. That there's a sort of a global behavior which is varying with the solar cycle. So it would be really interesting to compare.
Yeah, actually that's because I also worked once with Macintosh database and they have like this huge database of filaments and all those stuff. And I was thinking because we already have like the sunspot time series or from RGO or RGO database like during that time. So if somebody can consider like the twist in a way they can model the twist. I mean, probably they can even mimic the what was like already recorded in the Macintosh database.
Yeah, that would be really interesting just to compare it. And so then I wanted to ask you, so going back to what you were saying about how you had the S cases, some of them were more releasing more free energy. So can you relate, and you were saying it had to do with the helicity relative to that background, and it was being away. Can you say that again, just because it didn't quite sink in terms of what you were just saying about how that global helicity may vary with the solar cycle?
Yeah, so the thing is, like, for the sign, I mean, there is a big, first of all, I mean, if we are considering a very strong helicity or like the strong twist, I mean, it immediately erupts, that we have found. So we are considering the cases where the twist is not that high, like suppose 0.1. So what we found, like for cases where the twist is the sign of the twist is according to the observed alpha. Suppose there is a case like in the northern hemisphere, the sign is positive, and we are thinking like if the in the background the sign is already like according to the hemispheric helicity rule, so that particular spot will not contribute positively in a way, like that will not contribute to increase the non-potentiality in that hemisphere. So in a way we are trying to say, okay, if we, because there are, as I was showing, there are few cases where the sign is like opposite than the hemispheric rule. So in those active regions, and if that twist is not that high, so in a way it will not positively impact in increasing the non-potentiality.
But would the opposite be true during the time in the solar cycle when the global field, if there is I realize that's a time when maybe there's not as many sunspots, would it then, with the opposite?
Yeah, so no. So if there are not many sunspots, so then like that will be the case what I was showing initially. So I also performed another simulation that was like more than 1 year long simulation, and that was quite close to the solar cycle. That was during, I think, 2016. We started introducing the sunspot, but then we hardly introduced, I think, 50 sunspots, 2016 till mid 2018, I guess. But then also we find, okay, there were few places where the hemispheric sign was like corrected, but it was not enough to, what can I say, like block the effect of differential rotation. So the emergence of sunspot is like extremely important, and it has, the majority of those sunspots should have the correct hemispheric rule, so that we can see like the hemispheric rule in the like other non-potential structures such as filaments and so on. Yeah.
Thank you.
Any more questions? And actually, I have a question. When you introduce the sunspots, do you also consider its longitude dependence, like active longitudes, those kind of things?
It's like so when we are introducing the sunspots, it's exactly like what is observed by or recorded by HMI SHARP database. So yeah, it's like the position of the sunspot is like absolutely determined by the database.
Okay, so that includes that system.
Yeah, exactly. So it's like as it is observed.
Okay, Sarah.
Yeah, I have another question. So you have a model then which allows you to add twist in with just a few parameters, for example, things like choosing the amount of twist and the sign of it and so on. You were saying you'd like to compare to observations, and that's quite interesting, because you'd probably want to compare to coronal observations, right? Just as a way of testing that you've actually put the currents into the corona in the right way.
Can you just elaborate a little bit? But like, so like honestly, I'm a bit new to this HMI data, like handling this HMI database. So currently, what I was doing is like, okay, so for example, for this particular active region, so HMI already provides one calculated mean alpha value, and from the simulation, I was calculating these quantities for that same patch. And I was trying to find the ratio between those two, like in an ideal case, like the perfect selection of the constant, the simulated alpha and the observed alpha should be one, like the ratio between those two should be 1. but that I didn't find quite a lot. I mean, maybe these are few results that I can show. This is like the sum of that result that we find for different constant for how many of those 100 active regions was showing like promising amount of like the promising quantity, like how the ratio was quite close to the 1. And there were actually, in fact, many cases where, okay, the simulated and observed alpha didn't match quite well. So actually, me and Anthony, we are actually still looking for a better quantity to compare with from the observation. So if you can suggest something, that would be great, actually.
Okay, so you're saying that the way you're tuning, you're fitting the observations, of course, at the boundary, the photosphere, right?
Mm-hmm.
But there's some uncertainty there.
Yes.
And so what I was saying was, if you have observations of, if you've created a coronal magnetic field, right?
Mm-hmm.
And if you could compare it to spectropolarimetry in the corona, you can get a sense of whether you've created a coronal magnetic field that is matching observations in the higher atmosphere. There's a paper you might look at by Marcel Corchado Albelo,
Okay.
a couple of years ago, and he's done some work. He's actually done some work more recently associated working with like Duncan Mackay as well. So we've talked about the global models, but he did a work using Yuhong's model of a flux rope and found an index of non-potentiality, the amount of, and showed a correlation between the Stokes polarimetric signals in the corona and the non-potentiality in a structure very much like what you're making with these sheared large solar crown type structures. And one of the things we've talked about is using observations from COMP or UCOMP or ultimately from Cosmo to constrain models of the coronal magnetic field, because they are basically providing information in the corona, because as you make these choices of your parameters at the base, you're going to affect the sort of structure that ends up in the corona. So I mean, there's a lot of, and there's various things you in the nearer term, you might even be able to use dekist observations of a localized region to see if you've reproduced that. But I think for your sort of models, a global type of observation could be really powerful.
Yeah, exactly. I mean, that's like, thank you for the information. I'll definitely look into those papers, because I was struggling quite a bit to match these two quantities, and I was aware of the fact that this observed alpha comes with quite a bit of error, because like we're taking the current, like taking derivatives and all those stuff.
Right. It's another it's another kind of a test that you could do to see if what the assumptions being made at the boundary, how they're affecting the corona. But yeah, we should talk more. Maybe get Marcel into a conversation, because I know he's interested in doing global modeling of this kind of non-potentiality. And you've got some wonderful cases where, for example, would his non-potentiality index increase leading up to the eruptions that you're modeling? And that could be something that could be looked at.
Yeah, sure. Yeah, that's like really, I mean, yeah, I will look into those papers, because yes, honestly, like I was struggling, but yeah. And another thing was like, this part was important because we are now doing like global simulations and to decide what should be the twist parameter. So we tried to figure that out with these 7-month simulations, and starting like individual active regions separately with like different values of C. It was like quite a bit of task, but still we couldn't like reach to any conclusion, like what is the perfect C. But yeah, I'll definitely look into those papers. Yeah. Thank you.
Any other questions? If not, let's thank the speaker, Prantika, for an exciting talk, and that led to an exciting discussions. And I know you wanted to meet in a small group with us, and I will let you know after I set up checking.
Yeah, sure. Yeah, I'll very much I would very much like to talk to you people, because like, as you know, so this current position will be over by the mid of next year. So I'm already looking for like my next like destination, you can say. So yeah, I would very much like to have discussion with you people.
And morning will be better for you. So I'll check when people are available. And
yeah, sure. Thank you.
Okay, thank you, Prantika.
Okay, thank you. Bye. Take
Bye.
care.
Can I just say one thing?
Sure.
Sorry, I was gonna say we also have there's like an informal kind of Friday meeting. I can send you an invitation to. It's at
Okay.
might be too late. I don't know. It's 3 p.m. our time. What time
It's
is it
all
now?
right. I mean, now it's like about to be 10.
Oh, okay. Okay.
But
So
it's all right. I go to sleep around 12. So
do
for
you mind
me,
just if you just leave your email in the message
maybe
box here,
message box. Yes.
and
Sure. Thank you.
I'll just send you an invitation. It's not. The thing is, I think that the people who typically come are not. We haven't had a modeler in a while, so I don't know. I don't know if it would necessarily be useful, but
No,
it would.
no, of course.
I'd like if I could get a chance, I could ask you a few more questions
Yeah, sure.
about just for my own. Just
So
for my own.
I have just like, can you read in the chat box? I have sent
Yes.
my email address.
Okay, sounds good. Yeah, I'll just send you an invitation to the to the
Okay.
Friday meeting.
Sure.
No worries. But thank you again for your talk.
Thank you.
All right, take care.